So today I'm going to focus on measurements that I've done over in France and also some collaborators in Germany, where we look at the ion dissolution mechanism in these single atom iron nitrogen carbon catalysts, focusing on oxygen reduction. But I'll give some introduction as well and some other works that I've done during my PhD. So proton exchange membrane fuel cells, the most kind of widely known application of them is within transport. So you can see here, this is an image of proton exchange membrane fuel cell car from Toyota that we have at Imperial. If you're a postdoc, I think you can actually request to drive it. So I think maybe I'll have a go soon. And if you look inside one of these fuel cell cars, you'll see something resembling the schematic. So on one side, you have hydrogen fed into the anode, and then on the other side, you're converting oxygen with your protons to produce water at the cathode. And from this, then you get electrochemical energy. The problem with these fuel cells is mainly due to the oxygen reduction reaction. So this is where you're converting your oxygen into water. And if you look at your potential versus current density curve, you can see that most of the losses, so this is an overpotential, which is the same as a loss. You see that most of it is coming from the oxygen reduction reaction when you break out the different components of the fuel cell. And so this is really what the focus has been in terms of trying to advance fuel cell technology. And so if you look at scaling up this technology to say 5,000 fuel cell stacks per year, you see that the main limitation is the cost of the catalyst, specifically the cost of the catalyst for oxygen reduction, where we're using platinum-based nanoparticles, which then drives up the price of the catalyst. So there's a lot of work being done trying to find alternatives. And obviously it makes sense to try and move away from these precious metal catalysts, which obviously have a low annual production and a very high cost per kilogram, moving towards precious metal-free catalysts such as cobalt, nickel, or ideally iron, which is the lowest cost and the highest annual production. Unfortunately, if you then try and make single atom catalysts, we see that the most active of these is iron. So this is quite promising since it could potentially lead to a really low cost and similar activity to platinum. And just to clarify for those of you who aren't electrocatalysis people, so this is essentially a volcano curve where we see the binding energy to oxygen reduction intermediate and how this scales with the binding energy. Ideally, we want to be as close to the top of the volcano as possible, because then we're limiting the loss of the reaction. And ideally, we want to operate at around 1.23 volts. That's the theoretical potential. But there's always some loss in the reaction due to scaling of intermediates binding. And so normally we're operating at, say, a loss of 0.4 volts. So at the moment, if we're trying to replace the platinum-based catalysts, as we've seen, the most promising is these iron single atoms coordinated to nitrogen. And these look something like the schematic shown here. And so we've done some work recently where we wanted to also consider not just the economic factors, but also the environmental factors and the benefits that could be arising from using these iron-based catalysts. So here you can see a summary of an analysis that we did where we compared a platinum carbon catalyst where typically you have around, say, 20 grams or 10 grams of platinum in a fuel cell car, and the equivalent amount of iron nitrogen carbon catalyst is around an order of magnitude higher. But the cost of producing that catalyst, so shown in the green, orange, and purple here, is about the same actually as the platinum carbon catalyst based on current performance. But then if you start including the environmental impact of producing that catalyst, we see that we actually have a much lower environmental cost for the iron nitrogen carbon catalyst, and this is due to mining of platinum having a really significant environmental impact. However, ideally you should be recycling your platinum, and that can obviously significantly reduce both your both your processing costs and also your environmental costs. So if we want to compete with platinum recycling, we really need to reduce the amount of iron, nitrogen, carbon, and also consider different synthesis methods. But this is just to show that there are some benefits in terms of the environmental cause for these catalysts as well. And so, considering commercialization, one of the other benefits of these precious metal-free catalysts compared to platinum is they have this poison tolerance. And so this has been introduced before by Anthony Kushnak, where they found that these types of catalysts are less prone to poisoning from contaminants in, say, your feed compared to platinum. And so there's specific examples that have already been employed where if you have, say, a very poor quality air in the case of a fire and you want to have a backup power supply, it would be more beneficial to use these non-precious metal catalysts. And that's actually being used in a case in Japan. But ideally, what we want to do is really scale up this technology and use it in, say, transport applications. And in those scenarios, then you really need to consider a really long lifetime of your catalyst. So you see in the top right here, this is the ultimate US Department of Energy target. So this is running for, say, 5 years. And ideally, over that time, you just want around 10% degradation of your catalyst. And just for comparison here, you can see a state-of-the-art iron, nitrogen, carbon catalyst can operate for several months, but this is with 100% degradation of the catalyst. So we're still over an order of magnitude off where we need to be if we want to use it in, say, transport applications in a car. And so the way that these materials can degrade is, well, many different ways. You can have support modification, so carbon corrosion, carbon oxidation. You can have protonation, or alternatively, you can have degradation of the specific active site. So you can have the iron dissolving or aggregating into nanoparticles. So there's really a whole host of different ways that these materials degrade, and this is why they degrade so fast. But it's been found from the literature that there's a general consensus that the way that these catalysts mainly degrade to begin with is from this ion dissolution mechanism. And so what we really wanted to do was study this further and understand what's going on. But before we did that, we needed to make a model iron, nitrogen, carbon catalyst that purely consists of single atoms of iron in a nitrogen carbon framework. And this is not so simple as it sounds, and I'll go through why that is. So Alan from our group previously, you can actually use a bio-derived source such as hemoglobin. So you can see here your iron is coordinated already to your 4 nitrogens, and you can use this as a precursor to make these single atom catalysts, as he showed in this paper. The issue with using these bio-derived catalysts is you end up, in his case, with a very low iron, nitrogen, carbon density. And so this really would limit the performance of the catalyst. And if you want to load more iron in, then you end up having some issues. So if you mix your iron, nitrogen, carbon catalyst with a high amount of iron, you'll end up forming different atomic species other than just single atoms. So you have, at high temperatures, carbothermal reduction. So once you go above 600 degrees, you'll be forming, for instance, iron carbides. And these are species that we don't really want in the system because, one, we're not then making a model system, but two, these can lead to different degradation pathways and also parasitic reactions. And so we can alternatively do a high temperature pyrolysis with just our nitrogen carbon and then load our iron at low temperature, but still we're lacking a template for the active site. So we still end up with a distribution of different types of sites. And so what's been proposed in the last few years is to instead use this active site template method. So you use a templating metal which doesn't undergo carbothermal reductions at high temperatures and can also form these atomic species that coordinate to nitrogen. And then at low temperature, you replace this templating metal with an iron and then you can end up with your atomically dispersed ion species. And so the most commonly used method to do this is by using this precursor ZIF-8. So this is a crystal which consists of zinc atoms coordinated to 4 nitrogen. And this is suitable as well in terms of carbothermal reduction. It doesn't go undergo these reactions at the typical pyrolysis temperatures. And so you can take this ZIF-8 crystal structure, pyrolyze it, and then load your iron or your active metal at low temperature, and you can end up with purely atomically dispersed species. And the benefit of this is this ZIF-8 structure has a really high concentration of zinc, so then you can end up with a very high concentration of active sites. The problem is, what's been shown in the literature is that the electrochemical active site utilization is less than 10%. So while you can have a very high number of active sites, you're not really utilizing most of them. And this comes from the fact that this type of ZIF-8 structure is just purely microporous. And so you limit the accessibility of the active site, since you need a combination of mesopores and macropores as well to really open up the pore structure and utilize ideally all of your active sites. And so as an alternative method, what we looked at previously is adopting this approach that was proposed by Tim Ferlinger's group, where they use magnesium as an active site template to form your single atoms, but also as a porogen. And so you can take some organic monomer and mix this with magnesium chloride hexahydrate. And then you can undergo a liquid state polymerization, where you're forming magnesium oxide as a hard template, but then also you're forming around those some graphene-like carbon planes. And then you wash this with acid and you end up with this very open pore structure, and also with atomically dispersed magnesium coordinated to nitrogen. And you can see actually, just from looking at biology as well, that we know that magnesium can coordinate to nitrogen in this N4 configuration. When you look at chlorophyll, the active site there is this magnesium with 4 nitrogen. So this seems like a really promising method to end up with a very porous structure that's not just microporous. And so what we did is we took this precursor called triaminopyrimidine, or TAP for short. So this looks just like melamine, but with 1 less nitrogen, and doesn't just go straight into evaporating. Instead, it forms a liquid before evaporating at high temperatures. So you end up with this liquid phase reaction during the pyrolysis. And so what we did is we mixed this with our magnesium chloride hexahydrate, which is our hard template and active site template. And we pyrolyzed this between 800 to 1000 degrees for 1 hour, wash this in acid. We end up with this material called TAP, X denoting the pyrolysis temperature. And then we load our iron at low temperature, as I mentioned before. So we did this with a methanol reflux method at 90 degrees with iron chloride, and then afterwards we wash the material in acid. And the very interesting thing about this material is we end up with incredibly high surface areas and porosity. So we end up with over 3,000 meters squared per gram from the DET analysis, especially for TAP 900. And we see that as we increase the pyrolysis temperature, we see an increasing amount of mesoporosity and decreasing amount of microporosity. And normally these types of catalysts, they're say just dominant in microporosity or just mesoporosity, but here we have quite a suitable amount of a mixture of the two. And so this enabled us to develop, from the STEM imaging, we could see that we just end up with atomically dispersed species, confirming that we just don't have any nanoparticle formation. And in terms of the active site utilization, so we found when we compared to literature that we could obtain around 50% utilization of the active sites, which was above what was previously been recorded. And we can also obtain this while having a relatively high active site density. So we could have a high utilization of active sites and a high number of active sites. Whereas you can see in the literature, most materials have around 10% utilization. So now we've confirmed from our previous work that we could have this really porous material where most of the active sites, if we probe them, will actually be used in a reaction. And so we've made our model iron nitrogen carbon material. So now we can actually go on to the title of the talk, looking at the iron dissolution. So what we did first is conduct measurements with this flow cell ICP-MS. So in this configuration, you have your electrolyte, which is being pumped through this flow cell, and you have either, say, argon or oxygen dissolved in that electrolyte, and that's going towards your catalyst layer and then goes straight through to your ICP-MS. So with this method, you're just dissolving your inert gas or your active gas into the electrolyte. And this, unfortunately, for oxygen, which is our reacting species, really limits the current density, which we'll see in the next slide. But still, it is interesting for a model system study to really understand what can happen. And so this is the protocol that we used. So we did all the measurements in 0.1 mole of the chloric acid. And we initially conduct a 50 cyclic voltammetry in argon to kind of cleanse the surface, as we see in the next slide. And then we do 6 CVs in argon, 6 CVs in oxygen, and then we do a short accelerated stress test for 1 hour, and then we do some CVs afterwards as well. And just to say, the reason why for the accelerated stress test, or AST, we go between 0.9 volts to 0.6 volts. And this is trying to follow a recently established protocol for testing these iron nitrogen carbon catalysts in a fuel cell. So first, looking at the initial 50 CVs in argon, we can see here, this is on the bottom, measuring from the ICP-MS, how the concentration of our metal is being measured over time. And then in the middle figure is just our potential as we go from 0.9 to 0.2 at 50 millivolts per second. And then the current density, this is in argon, so we have a relatively low current density, and this is just coming from capacitance. So we can see, looking at the magnesium, which we use as a template in the material, we see that this doesn't seem to be varying at all as we change the potential. And so we didn't really focus on this any further. Instead, we just look at the iron, and we can see that over the first 50 cycles, we see this exponential decay in the iron dissolution. It seems to stabilize once we've hit around 50 CVs. So we can see that during this time, we seem to be kind of cleansing the catalyst of some very unstable iron species. And then we move on to the 6 CVs in oxygen and argon. So you can see from the ICP-MS that we actually measure very similar signals under argon and oxygen. The difference between the two is when you look at the current density. In oxygen, we're conducting oxygen reduction, so we're generating some current. But you can see here the current density that we're getting is around -1 milliamp per centimeter squared. So this is really a small current, and this is limited by the solubility of oxygen in the electrolyte. But the interesting thing is, if you then do an accelerated stress test, so you're sweeping the potential from 0.9 to 0.6 volts, holding it 3 seconds at those potentials, you see something a bit different. You see that in oxygen, we have a greater iron dissolution compared to argon. And you can see as well, again, we have, as you expect, a slightly higher current density in oxygen as we're converting oxygen to water. And then if you look at the chronoamperometry, so this is holding the potential during the 1 hour measurement, we see that as we step the potential from 0.9 to 0.2 volts, we have a really significant spike in the iron dissolution, whereas when we go from 0.9 to 0.6, we have a spike, but to a less degree. And we see from the current that we still end up with around the same current density, again limited by the solubility of oxygen. And looking at post-mortem characterization, we couldn't really see any large particles of iron after this AST protocol in argon or oxygen. And so from this kind of measurements, it seemed like there wasn't really too much difference going on between the argon and oxygen measurements. And so what we wanted to do was try and test this in a more practical device. And so what you can do here is use a gas diffusion electrode system. So this is much closer to mimicking a real fuel cell. So in this system, you'll have your oxygen or argon flowing along the backside directly, which can contact the catalyst layer. So you can end up with much higher current densities because you're not dissolving the oxygen in an electrolyte. You can ideally access the site directly. So you have your argon or oxygen on the backside, your catalyst layer here, and then you have an electrolyte where your ICP-MS is then withdrawing sample over time, and you're analyzing the metal concentration in that electrolyte. So this is a setup that has been developed by Sergei Cherevko's group in Germany. And so again, we took a similar protocol of using 0.1 molar perchloric acid with our TAP 900 material. And we do as well the measurement at 70 degrees in addition to at room temperature. And to summarize the protocol, so we saw from the flow cell that we need to do at least 50 CVs to really stabilize the measurement. So we do that first, and then we step the potential and the current down from 0.9 to 0.5 volts in this initial part. And then we do a short accelerated stress test, again going from 0.9 to 0.6, holding at that potential for 3 seconds. And then afterwards doing the same measurement. And yeah, as I mentioned before, we do this AST protocol to try and mimic what's now being proposed as the standardized method in testing these catalysts in a fuel cell. So if we look at the current density initially, we can see something very different to the flow cell. We can actually obtain relevant current densities for a fuel cell. So we can get up to 100 milliamp per centimeter squared. So this is 2 orders of magnitude higher than what we can get in a flow cell. And we can see that when we measure the pristine material, after we do the argon protocol, so the argon AST, interestingly, we actually saw a slight improvement in the performance. So we see the potential for the same current density is higher. So that means less over potential. And this is being proposed to come from the fact that over time, the catalyst surface gets wetter. And so it allows the electrolyte to kind of go deeper within the catalyst layer. So we're proposing that that's probably what's happening during the argon protocol. Whereas in oxygen, we can very clearly see that there seems to be some degradation of the catalyst, as we see the potential for the same current density is shifted by around 50 millivolts. And then looking at the measurements, sorry, this should say 75 degrees, we see, as you would expect, for the pristine material, performance is better at high temperature, but we have even more severe degradation of the catalyst, as we see the potential shifting by more than 50 millivolts. And so if we look at XPS, we can see some clear differences in the pristine material compared to the 75 degrees protocol. We see there's an increase in the amount of oxygen surface functional groups, whereas in the argon and oxygen at 20 degrees, we don't see any clear difference or a less significant difference to pristine material, suggesting that it's only after the AST at 75 degrees that we have some surface oxidation, which can limit or change the turnover frequency of the catalyst, whereas at room temperature, we don't seem to see any surface oxidation. So the degradation under 20 degrees should just be coming from ion dissolution, we propose. And so looking at the pristine material, we can see still that the iron is atomically dispersed, and we don't really see any nanoparticles within the material. So once we've made the electrode, it's still atomically dispersed. And after the argon protocol at 20 degrees, we see that it's still mainly atomically dispersed, but we do see some areas of iron and oxygen overlapping and some very small iron clusters. But these are a fairly low concentration. Whereas after the protocol in oxygen at 20 degrees, we see very clearly that there's a high concentration of these iron oxides, as we see the overlap of the iron and oxygen in EDX. And we see as well more clusters of very, very small clusters of iron in the material. And surprisingly, when you look at then the measurement at 75 degrees in oxygen, we see that there doesn't seem to be many visible iron particles within the catalyst, whereas we saw a much bigger degradation in the gas diffusion electrode performance. But I'll explain why this is in a moment. And so if we combine the data with the ICP-MS, so we're essentially combining what we saw before with the potential and current density, but we combine it with the iron concentration that was measured during these measurements with ICP-MS, we see some stark differences in the iron concentration during the measurement. So in argon at 20 degrees, as we're stepping down the potential from 0.9 to around 0.5 volts, we see very clearly that there's a significant increase in iron dissolution as we step down in potential. Whereas in oxygen at 20 degrees, as we step down in potential, because we're now conducting oxygen reduction, so we're generating current, you can see here the current is increasing. So as we get to around 15 milliamp per centimeter squared, we see actually a decrease in the iron concentration that's measured by ICP-MS. Whereas if we look at oxygen at 75 degrees, as we step down in potential with the same current density, we actually see initially an increase in the iron concentration and then a decrease in the iron concentration as we go to higher current densities. So this is kind of confusing, but I'll explain in the next slide what we think is happening. And then looking at the 200 accelerated stress tests. So we're in all the measurements, we're stepping from 0.9 to 0.6 volts. In argon, this is we're getting high current, but this is just pseudo-capacitance. There's no oxygen reduction taking place. Whereas in oxygen, we see that we have constant minus 50 milliamp per centimeter squared, and this is coming from oxygen conversion to water. And so again, we see some very stark differences between the three different measurements. In argon, we see this fairly consistent iron concentration increase over the measurement. In oxygen at 20 degrees, we see an iron concentration decrease over the whole period, whereas at 75 degrees, it seems to be relatively constant and a higher amount of iron concentration over the whole measurement. So again, very different. And finally, if you then do the measurement after the AST, so same as this measurement, but you've just done the AST, again, you see a similar sort of thing to here, except some parts are exaggerated. And this is, we think, because of a buildup of iron oxide in the catalyst layer during this AST. And so then when you look at, say, 75 degrees in oxygen, we have a more distinct increase in iron concentration here, because we're dissolving our built up iron oxide into the electrolyte. And you see that as well at 20 degrees, we have this clearer initial increase in iron concentration as we have this buildup of iron oxide formed in the catalyst layer, which then dissolves at low current density, but then starts forming iron oxide again as we go to higher current density. So this is quite confusing, but I'll keep going and hopefully it'll make more sense once we talk about the Poor-Bay diagrams. So going back to A-level chemistry, hopefully everyone remembers Poor-Bay diagrams. Again, we have, this is just the initial GDE ICP-MS measurement in argon. So we see this, as we step down in potential, we see this very clear increase in the iron dissolution. And this increase in iron dissolution seems to occur at the potential where we go from iron 3+ to iron 2+. So this is around 0.75 volts. And we see here as we step down past this 0.75 volts, we see this very clear ion dissolution increase. So it seems to be following that as we go from iron 3 plus to iron 2 plus, we have a greater dissolution of iron measured from ICP-MS. And just to say here, this is a pore bay diagram taken from literature at 25 degrees. And we're looking here at pH 1 because we're using 0.1 molar per chloric acid. So then we look again at the 20 degrees measurement in oxygen, where we see as we step down in potential, the ion concentration actually decreased once we hit minus 15 milliamp per centimeter squared. So if we look at the pore bay diagram, we think what is happening from just looking at the pore bay is we go from this around 0.9 volts, and as we're stepping down in potential, the current density increases, and as we increase the current density, we're consuming more protons. So the reaction of oxygen reduction, just to remind you, you have 4 protons, 4 electrons, and oxygen, and you produce 2 water. So as we consume more protons in the catalyst layer, our pH can actually be increasing in the catalyst layer. And so that's what we think is happening from the pore bay diagram. And then if you look at 75 degrees measurement in oxygen, the pore bay diagram looks a bit different at 100 degrees because it's dependent on temperature and also ion concentration. So you do have to bear that in mind. But if you look at the pore bay diagram at 100 degrees, which is close enough to 75, you see that the pore bay diagram looks a bit different at 25 and 100 degrees. So as you step down in potential, what seems to be happening is when we have this small current density, so going from 0.9 to around 0.75, we have this increase in ion concentration at these low current densities, so around up to 15 milliamp per centimeter squared. So we seem to, at 15 milliamp per centimeter squared, we seem to have an increase in ion concentration because we're stepping from iron 3 plus to potentially an iron 2 plus region. And then as we go to high current density, we end up forming this iron oxide, which is why we have a decrease. And the reason why the concentration seems to be higher in general, we think, is just because of a faster mass transport of iron and also protons within the catalyst layer once you increase the temperature. So hopefully this makes sense so far. And so we wanted to explore this local pH change. And this has actually already been considered in the literature by some groups around 10 years ago, where they look at, this is essentially modeling just a single pore in the catalyst layer, where you have your membrane. So Naphthalon is a membrane which transports your protons. So you're going from basically a very proton-rich concentration. And if you modeled, in their case, they modeled a platinum wall. And as you go from Naphthalon to a pore that's filled with water, so this is like a mesopore, like 10 nanometers wide. As you go from this proton-rich to a proton pore, you obviously will then have this significant pH change within a pore. Now, this is just considering a single pore, not a whole catalyst layer. So we wanted to consider what's happening in the whole catalyst layer. And so this was developed by a colleague in France, Antoine Bonnefond, where they developed just a very simple microkinetic model where you have your catalyst layer. And we measured this, which is 60 microns thick. And then we have our ICP-MS detector, which was only 150 microns away from the catalyst layer. And then because we're using a gas diffusion electrode setup, on the back side, we have our argon or oxygen. So this is essentially how we display the model. And again, just to show you, this is the initial gas diffusion electrode measurements. And I've just converted here, this is ion concentration in 10 to the minus 6 molar. But it's still the same values as before. And so Antoine developed this model, and he tried to semi-quantitatively replicate what we saw in the measurements. So you can see here, this is the ion concentration over time, where we see, in this case, he developed it based on the argon measurement. So we can see as we do the measurement over time, it increases by around Mach 1. And we can see that he's able to replicate this by varying different values, such as the void volume of the catalyst layer, or also the proton consumption, so the rate of proton consumption in the catalyst layer. So you can see that he seems to be able to model what we saw in argon quite well, and this validated the model, so then we could then match that with the measurements in oxygen, varying the values. And we see that when we look at the catalyst layer, so going from this side is 0, this side is 60 microns, we see that in argon there seems to be a bit of a distribution in the ion concentration, whereas in oxygen it's fairly constant. And the really interesting thing is, if you then consider the concentration of protons or the pH, in argon, obviously, as you expect, there's no consumption of protons because there's no reaction happening. So we just have a pH of 1 because that's the pH of the electrolyte. However, if you look at the measurement, sorry, I forgot to say, we're looking here at the measurement in oxygen, replicating the measurement at minus 15 ounces per centimeter squared. So we're really focusing on this interesting region here. So when he developed the model, he found, depending exactly what parameters you use, but in general, you see that there's a very clear increase in the pH as you go deeper away from the electrolyte in the catalyst layer. So you can see that we're reaching pHs of around 8.5 to 9 in the catalyst layer on the side nearest to the supply of oxygen. And so this is really interesting and hasn't really been considered before. And so if we again look at the Paul Bay diagram at 25 degrees, we see in argon, we're just stepping down in potential from ion 3+ to ion 2+, whereas in oxygen, we're, depending where you are in the catalyst layer, you're either in a pH around 1 at the interface, but as you go into the bulk, you're in this region of ion oxide formation. And another thing I wanted to add is the AST measurement. We saw that there's very clear differences depending on the conditions of that protocol. And so it's really important to consider basically every condition that you have completely changes what you'll see then afterwards in the catalyst layer. And so for the conclusions, we were able to synthesize single atom ion action carbon catalyst with greater than 50% utilization of the active site. And we saw that depending what you use, so like a flow cell compared to a GDE, or 20 degrees versus 75, or argon versus oxygen, everything changes, everything matters, and everything's different. So comparing flow cell to GDE is, you can't, and doing flow cell measurements, I'd say, is pointless. In hindsight, I think you really just have to go to practical devices, really. So we're able to, well, I didn't, but Antoine developed a microkinetic model based on the results. And we saw that there was a significant increase in the pH. And there's some important implications for that. One is that there's a distribution of different ion species in your catalyst layer. So depending if you characterize the interface or characterize the backside of the catalyst layer, you'll see different things. And so this explains, I think, partly why there's some conflicting post-mortem observations in literature, because it really depends where you're characterizing the catalyst. And also, importantly, it's quite clear that we must be underutilizing thick catalyst layers. So these ion action carbon catalysts, they're typically around 60 to 150 microns. So we use 60 here. So if people are using 100 micron thick catalyst layer, most of that isn't being used because the pH is increasing significantly. And so this is really limiting the performance of the fuel cell. So then the question is, where do we go from here? So this is essentially, on the y-axis, this is the volumetric site density, so how many sites you have per volume, versus the turnover frequency at 0.8 volts. So this metric is important when you want to consider transport applications, because you're really limited by space. So you want to consider the number of sites that you have per volume. And so we can see, if we look at a platinum on carbon catalyst at 47 weight% of platinum, we see that the volumetric site density is over an order of magnitude higher than what we have in the state of the art for these iron nitrogen carbon catalysts. And then if you look at the turnover frequency, they can actually be comparable initially, these iron nitrogen carbon catalysts. But ideally, if we want to improve the turnover frequency further, we probably need to develop a different type of active site. So if you again go back to biology, you see that the most efficient enzymes for oxygen reduction is cytochrome C oxidase, and this can have a turnover frequency an order of magnitude greater than what we currently have. So we either need to increase the site density or develop a new type of active site, or ideally do both and also make it stable. So there's still more work to do for PhD students, fortunately. And there's also different applications for these iron nitrogen carbon catalysts. So Jesus has done a lot of work developing them for CO2 reduction. So you can very efficiently make CO from CO2 with these single atom catalysts. And in that work, they found that if you use our same catalyst, this TAP 900 with iron, we can achieve in line with state-of-the-art performance compared to silver or gold, which are the commercially used catalysts for CO2 reduction to CO. And so there's other applications of these catalysts beyond just oxygen reduction. And so with that, I'd like to thank you for listening, and particular thanks to Jesus and Ethan and Magda for their help in all the different works, and also for the GDE ICP-MS work. This is really a big collaboration with France and Germany to get this done. So with that, I'd like to thank you for your time and welcome any questions. And hopefully it made sense. It's complicated. Yes.
So I guess thank you for a very good talk. That's really good. So you talk about how different your results are, kind of going from a flow cell to a GDE.
Yeah.
I guess you go about further down the line, going from a GDE to an actual
Fuel cell.
Fuel cell.
Yeah. Yeah. I mean, this is
how different do you think that's going to be?
Yeah, this is the question. I mean, in a fuel cell, you're in a GDE, there's no we didn't use they did use a membrane, but you're not under compression. It's a complete, again, probably a different system. You're probably going to see different things. But I think what we see in terms of this pH distribution, I think will still hold in a fuel cell. But it would be interesting to prove if that's the case, because yeah, it is a different system. People are moving towards trying to replicate in real device with characterization, but it's always difficult. But yeah, you could put in the exhaust of the fuel cell as you generate in the water, you could try and hook it up to ICP-MS, but it's difficult. Yeah, maybe someone will do it.
I'm obviously very familiar with the work, but every time we talk about it, new questions arise because there's a lot of information. So in particular, I was less familiar with the microkinetic modeling. It's very interesting that they can approximate a pH of like 9, 10, closer, like probably in the inside of the pore. So does that mean that essentially the way the material degrades will be similar to the way it will degrade in alkaline? With the pH is similar?
I think there won't be any. So with the pore barrier diagram, you have to consider that this is the potential versus SHE, not versus RHE. So say at the potential of around 8.5, if you then convert that with the scales, this is essentially your oxygen reduction to water. So the over potential would need to be very low. So basically there's no reaction happening here because this is the equivalent of 1.23 volts versus RHE here.
Okay.
Because this is versus SHE. So basically you're not using like this part of the catalyst there.
Yeah,
There's no oxygen reduction. So yeah, it'll be this maybe the same degradation in alkaline in argon. That makes sense, where there's no reaction. Yeah.
Then you will just, then essentially you need to, that you have like a bunch of protons, then the protons, then the deflation, and then
Yeah.
so then will that count as catalyst being utilized if there is no?
No, yeah. So like the catalyst, I don't think is being utilized. Basically, as you're increasing the pH, then you're shifting the potential closer and closer to the potential for oxygen reduction. So I say from like anywhere from say pH 5 is maybe not being used. So then, yeah, like over half your catalyst layer isn't being used. You're just using this part. So yeah, I don't know if we want to make 100 micron thick catalyst layers. It's
Then
difficult.
you have like proton shuttles like they do in the nitrogen reef, and that can improve something or not really.
I mean, the issue is your protons are coming from the anode side, so like they still need to get across somehow.
I was thinking not in a nitro.
Yeah. Maybe in a GDE or something, but
Yeah,
not in a fuel cell.
super nice.
Something about how you have to wait until it's stable reading.
Is this in the flow cell? Oh, sorry, went too far. Okay. Did you mean? Okay, so basically, in the flow cell, we did 50 CVs in argon because and then we see there's this like exponential decay where there seems to be some unstable ion species, and so then we said, okay, in the GDE we'll do the same protocol because we see there seems to be some unstable species. They didn't measure the ICP-MS during the 50 CVs initially in the GDE, mainly because the concentration was so high that you hit the limit of the detector, so that you can. The reason why we didn't show the measurements in argon at 75 degrees is the ion concentration was so high it was above the limit, and it was like you can't run the measurement. Yeah, you're removing like some unstable ion species. Yeah. I'm not sure in the flow cell it's just flowing. In the GDE, I don't think they replace the electrolyte. So again, this maybe explains why there's differences in like the baseline concentration. Yeah. Yeah, so it's like it's kind of known in the literature for these catalysts. For any electrocatalyst, normally you do some preconditioning step, but people never know, especially for these ion nitrogen carbon, if your preconditioning is killing the catalyst or activating the catalyst or doing nothing. It depends on the catalyst. But yeah, always for electrocatalysts, you do some preconditioning. I guess in the battery, you probably do some the same. I don't know. Yeah.
Which also like very porous ones, and then you can have some bubbles.
Yeah.
Thanks for a really good talk. I think the pH distribution of the board is super interesting. I was wondering, because you mentioned that when you were synthesizing a TAP compound, that you increase the temperature, you kind of increase the portion of mesopores compared to micropores. And do you think that would have, so the question is, but do you think the size and shape of the pore would help maybe even out the distribution of pH and maybe even make it specific to a pH you want?
Yeah, I mean, it definitely have an effect. So we saw when we changed the void volume, so the epsilon, in the microkinetic modeling, we see it has like an effect. but still you end up with the same sort of result. So here, well, here I don't show the different epsilons. I just show different proton consumption. But yeah, if you have a different epsilon, which is your void volume, that would change if you have different amount of mesopores, or for example. Yeah, but also we found, well, not I found, but the group in France have found that depending on the type of pore that you have, some people, if they just have micropores, you end up with different. You end up with just iron oxides. If you just have mesopores, for some reason you end up with just iron particles. In our case, we have micro and meso. We end up with iron oxide, but there seems to be some effect as well of like the type of pore that you have here. Great. There's no more questions, and we can stop there.